When I was a child, my most delightful dreams were about flying. I'd be walking along, and slowly I'd feel lighter and lighter on my feet before taking a step into the air. But I would just hang there a few inches above the ground. Achieving real flight, it required a certain mindset. I find it difficult to describe in words, but I did something in my head, almost bringing forward a feeling of quietness. And then there would be this really weird tingling at the base of my back. And I knew I could soar up to and beyond the clouds, and I would. Now, I know many people have had this dream in one form or another. Maybe most people do. Maybe everyone. Strange, isn't it? The wish to soar like birds inspired those pioneers who sought solutions to the aerodynamic and control issues of flight. Now, the Wright brothers gave it a really good shot, but the concept of a continuously shape-changing wing, like that of a bird's, was really beyond the technologies of the day. And in essence, what evolved out of our capabilities was a rigid wing with a set of flaps connected using standard hinges and pivots. And this is what we have used for the vast majority of commercial and military aircraft to this day. Now, we've gotten very good at making wings from this template, and one could easily believe we've near-perfected wing design. But the template we've been using is an historical fossil, and the wings we designed from it do absolutely no justice to what nature has achieved when considering flight. Now, there are many factors that need to be considered in the design of a wing: the twist, the sweep, the taper, the camber, the aspect ratio, anhedral, dihedral, a whole range of things. And typically, these variables are built in as static. So in essence, we have a rigid wing. Camber is the only real exception here when considering flaps, but they do a pretty poor job of it relative to birds and other flying animals. So we have a rigid wing. And for the last 100 years, we've been building these wings to resist loads. In nature, wings are built to conform to loading. Now, the capability of varying these variables that we have designed as static is what we call morphing. And if we could do such a thing, we could design one aircraft to fulfill the role of many, whilst doing a better job than any of them at it with regards to overall efficiency. So not only would we have aircraft consuming less fuel, but there would be less of them around, as the vast array of aircraft out there, all the families of aircraft out there would be condensed into a few multidisciplinary vehicles. Now, here I've got a Hawk in a high-speed agile configuration and a low-speed, highly efficient cruise configuration. And this is reflected by the two aircraft. But as they are compared to each other relatively, the refuel plane can never be agile, and the fighter jet can never be fuel efficient. So what is going on in the field of morphing? There are companies out there, and there's no sound. There are companies out there embracing biomimetics into the development of their products. And one of these companies is Festo, a supply and automation technology. Now, these might just come across as novel toys, but much of the knowledge that is gained in developing these prototypes is devolved back into the products they produce. This is revolutionary stuff, and it's going to set the way for incorporating bio-inspired design into real-world fuel-saving application. So flight is quite noisy, not just because of jet engines, but because of the behavior of the air as it travels over the thing flying. I'm sure you've all heard a pigeon whooshing over your head. Owls, however, have developed this really unique capability of gliding nearly silently. And it's to do with manipulating this airflow over their wings with these little serrations that they have on some of their feathers. Now, this serration concept has been employed by a few groups out there and has been put onto turbine blades and onto conventional wing geometries. And it works really, really well without having any notable impact on the aerodynamic efficiency. If we take a look at these two graphs here, they show the nature of the airflow from the front of the wing to the back of the wing. The top wing there hasn't got the modification on it, and the bottom one does. Now, if we use an analogy, if we consider the air as if it's a quiet ocean rushing up over a beach, and those colored splodges as if they're loud, crashing waves. Well, actually, in reality, there's no real difference between the ocean and the air with regards to the behavior. But as you can see, these splodges have been reduced significantly in scale. These waves are much smaller and so less loud. And so we have a more quiet aircraft. Airbus is looking into developing a silent aircraft. And on top of tucking in their jet engines above the tail, such that there is a barrier between those engines and us on the ground, they're also looking to employ the serration technology into the leading edges of their wings. Considering the honeycomb, as a structural concept, it is tremendously sturdy for its mass and has been employed in reducing the weight of aircraft for some time now. And also considering the anisotropic behavior of the skin of a bat's wing, as in its stretchiness in one direction but lack of stretchiness in another. This has been known for some time too, but the combination of these two concepts very recently has allowed for a new honeycomb structure to be developed, and it maintains the structural strength that the normal honeycomb does, but it's stretchy in one direction. And in the field of wing morphing, the research groups out there have realized this is a tremendously powerful tool. Here we have a wing in its compressed state and expanded state. Remember how I was showing you that Hawk with its agile configuration and highly energy efficient cruise configuration? So it's interesting stuff. There are groups out there, including NASA, that are working on morphing wing aircraft. And this recent breakthrough with the honeycomb is likely going to accelerate concepts like these into reality. If you take a look at the dragonfly wing at the top there, it seems that a truly bio-inspired wing design has the look of complexity about it, but is actually based on very simple underlying principles. There are no smart gizmos inside that wing making it morph. The wing itself is simply smart through the distribution of the vanes, the structural vanes, and the types of hinges interconnecting them. Now, taking a look at the insect wing here, and the diagram below it, which is just a simple representation to clear it up for you. Below that, we have a computer-generated model of a wing that has the same morphing characteristics as the insect wing. But as you can see, it's a fair bit more complicated and weighty than the insect wing. But if you look below that wing, what we've done is apply a genetic algorithm to it such that it optimizes the shape of the wing, the size of the wing, the distribution of the structural vanes inside it. And if you compare the bottom wing to the top wing, or the diagram of it, look how similar they are. Billions of years of evolution have developed that wing at the top, and man has tried to mimic it with these genetic bio-inspired algorithms. You can see here on the left, on your right, there's this genetic algorithm has been employed into the leading and trailing edge of a typical wing to help it morph. But it's not just genetics and evolution that inspire our optimization techniques. There are a whole range of patterns in nature that we look at: bee colonies, ant colonies, viruses. Boeing have a very well on its way concept, the blended wing body, and it's benefited from these genetic algorithms in reducing the weight of the aircraft by optimizing the the skin of the wing itself, the distribution of the plies and laminates. Okay, so I've given you a little taster on what's going on in the field of morphing right now. And rather than desensitizing you to more of these great ideas, I'm going to show you a little video I've made. I've compiled footage from a whole wide range of sources. None of it's mine, but I hope you like it. Now, what I hoped to show there was how nature has conquered this concept of flight in a vast variety of forms, and also to show you what man has achieved in a practical sense so far. Now, biologists tell us engineers not to be limited by nature, and we shouldn't. But there are a vast variety, a tremendous amount of patents hidden within nature. When it comes to my research, I've never been more humbled. I've never felt further from my goal than when standing right next to it, when, say, watching a pigeon as it takes off in front of me, or looking at a fly land on the ceiling above me. There is so much we don't know. Quoting a big hero of mine, Richard Feynman, I think nature's imagination is so much greater than man's, she's never going to let us relax. Man is a unique creature among the animals. Once lost within the depths of the ocean that is life on this small planet, adrift to violent torrents, he was gifted with a set of traits that enabled him to come out of the obscurity. Man was the first to seize control of his place within these torrents, and has also become the shaper of what is now his ocean. Quoting another hero of mine, Charles Darwin, a man thinks himself a great work, worthy of the interposition of a deity. More humble and I think truer to consider him created from the animals. To the best of our knowledge, it's taken the universe 13.72 billion years to evolve to this point. The universe is now self-aware through us. If we condense the cosmological time of our universe down to a year, with the end of the year being now, modern man, as in since the invention of radio or since the invention of the airplane, modern man has only been around for about half the time it takes to pronounce the final digit in the New Year countdown, a little less than a quarter of a second of that year. Our arrogance, our dogma, our greed is culminating to another mass extinction. Will we grow out of our adolescence as a civilization, or will we simply snuff ourselves out alongside everything else? If there's one thing I've learned worth mentioning, through what my research has opened me up to, through the various cultures and traditions I've experienced in the now 5 countries I've resided in, from the sand bushmen of the Kalahari to the intellectuals in the ivory tower, I've come to realize that these tremendously intricate wonders around us transcend everything that divides us. Thank you.